Hello, this is the first live interactive session for the course Structural Geology offered by NPTEL. And my name is Rajiv Mukherjee, and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. So I will be hosting this live session for the upcoming 12 weeks during the tenure of this online course. And the main uh, idea of having this kind of interactive session is to gain a more profound understanding of the subject that you are learning through this online course, also to solve some problems associated with structural geology and overall earth sciences as well. So now, to talk about the objective of this course, that is the structural geology, I'm sure that you all have gone through the first week lectures, which was the introduction or the basic concept of structural geology. But as you know that this is a 12-week long course, and there are many topics that will be covered during the entire course. The instructor, Professor Shantanu Misro, will talk about many things that are relevant for structural geology, tectonics, geodynamics, as well as for other branches of geology such as petrology and sedimentology as well. So I can highlight some of the objectives, important objective of this course is to provide a general overview of the subject and to develop the basic concept. So this is the primary goal of the first week that you have gone through. Now, the second is to build up the skills for geometric interpretation and linking the geographical disposition of geological structures. So this is one of the most important feature or important uh, outcome of structural geology is to see the things, the geological structures in the field in uh, ranging from microscopic scale to hand specimen scale or macroscopic scale to outcrop scale, and even going to the regional or global scale. So there are structures which are repetitive and they occur in every scale, and the main idea of the subject and how it has evolved since the initiation of geology is to actually gain insights into the geometric modifications or their characterizations of different kind of structures, how to recognize them through geometry, and how the geometry changes with different rocks, different type of rocks at different uh, deformation conditions, and also in different geographical areas. So while doing a geological mapping or lithostructural mapping, we often talk about the geographical disposition of different kinds of outcrops. So linking one outcrop to the other is the main task of a structural geologist, to gain insight into the overall or the regional scale deformation that has been that has occurred in the region of interest. And also the third point is to develop a strong sense of scale dependence of geological processes both in space and time. So I'm sure that in the first week you all have learned about the importance of scale in structural geology, and especially when we talk about micro scale to macro scale to mesoscale and even to the global scale. But the important thing is that the scale is not only important in space, but it is also important in time, because the duration of each and every of these processes dictates how the outcome will often change, right? So there can be an instantaneous event, or there can be a very long duration event for millions of billions in years. Those can be those processes are generally known as quasi-static processes. So both of these processes have their different importance, and structural geologists deal with both of them, both kind of features: instantaneous, quasi-static, small scale or micro scale, even going to the nanoscale to the global scale. So the range is very, very huge, both in respect to space as well as time. Now another objective of the course is to develop an understanding of the different deformation processes and mechanisms that governs the formation of geological structures. So this is a very much interdisciplinary uh, point that we have to remember, that structural geologists often take help from different subjects such as most importantly the material science engineering, applied physics, mechanical engineering, mechanics, uh, chemistry, computer science for modeling, analysis, etc. And mathematics, of course, is the backbone of having the interpretations of these kind of deformation processes. So for a structural geologist to successfully carry out all these things, even from going to the field to analyze the deformation features, should have a very good grasp on the basics of different kinds of subjects, especially material science perspective, the physics of deformation, and the chemical composition of different kinds of rocks and how they control the viscosity of the rocks when they're deforming, as well as their mechanical interpretations, like whether the structures that are being deforming, whether they're stable or not. And also the often we say that structural geologists can play a very important role in uh, development of civic structures that are important to society, such as like dams or bridges or tunnels or even buildings, skyscrapers, or all these things. They require the knowledge of the deformation of materials over a very over a certain duration of time, and that's how structural geologists are also important for that perspective. And another is to connect structural geology with other domains of earth sciences such as petrology, geophysics, hydrogeology, ore geology, mining engineering, etc. So over the course we will also see that we will not only talk about the deformation mechanism of specific we will not only talk about the deformation mechanisms associated with different kind of structures, but we will also talk about which kind of rocks are responsible for these kind of deformation features that are readily visible in the field. Not all the rocks will develop all the structures that we see, and these kind of structures will also vary according to several thermodynamic parameters such as temperature, pressure, density, composition, etc. Right? And the finally is to provide an understanding of the lithostructural mapping. So this is one of the most important practical outcome of the course, is to provide you with the knowledge of how to carry out lithostructural mapping. Now this mapping is very much important aspect for having a good position in academia as well as industry, because geophysicists, exploration companies that involves geophysicists, hydrogeologists or mineralogists, they also hire structural geologists because of their knowledge of the deformation and associated mineral deposition, as well as the part where they know how to do or how to carry out lithostructural mapping. So I hope that all of you which who have taken this course in this online NPTEL course, they will ultimately be profited by this all kinds of knowledge, starting ranging from theoretical perspective to practical applications of structural geology, and it will be ultimately helpful for your future career. Now this was the objective of the overall course, but we have a different agenda for these kind of live sessions that will be carried out in each week. First of all is to clearing doubts on the course material. So these live sessions will solely focus on uh, because there are so many things will be covered during the course, starting from the basic concepts, then stereographic projections, rheology of the rock, stress, strain, all kinds of structures, and then mechanisms. So there will be a lot of things going on, and it is hard, it is very much difficult to grasp all these things just by looking into the lectures and having completed all these things within a week. And also you have to do the assignments. So my job here is to provide you with a certain assistance regarding the course materials that has been taught, to clear doubts on the materials, whether if there are any. Also discussing conceptual and numerical problems on structural geology that will help in solving the weekly course assignments. So I will specifically design this live session to be as much as possible interactive as it can, so that during this live session we can solve at least a few problems. We will discuss the problems, their origin, and we will also try to connect those problems with other several questions. And altogether I hope to deliver a very good I mean an archive of questions with numerical type and conceptual MCQ type. All those things will be there, so that you can perform well in your assignments and the final examination of the course, and also for your betterment of the understanding. And as I told, that I will be discussing multiple choice based and numerical type questions. Now the important thing is this kind of questions that I will be dealing with during this live session, those will be also relevant for national level competitive examinations in geological sciences like CSIR NET, GATE, and all those examinations, starting from any kind of recruitment processes or any kind of interview, or even for your own academic purpose where you are learning your undergraduate or graduate courses, right? And finally, to provide some glimpses of recent research directions in structural geology and tectonics, and discuss some future opportunities in research and academia. So as a as I am a Prime Minister's research fellow, this is my duty to carry out these kind of teaching duties online, to especially provide you with the opportunities in research and academia that I am currently pursuing. And I would also like to share my experience during my research tenure, and so that I can encourage uh, all of you, or who wants to pursue the academic career in future, they can also join in this kind of research activities. So that is how the live sessions will be. Apart from solving the questions that will be helpful for assignments, we will also delve into the different recent avenues of research in structural geology and tectonics overall. So this is the course outline based upon which we will carry out the live sessions. So starting with week 1, that is the basic concepts of structural geology. And in this week 1, I mean, which you have already finished, the basic concept of structural geology includes um, the idea of scale, homogeneity, heterogeneity, isotropy, anisotropy, different kinds of models of analyzing the structural observations, all those things that has been taught in the week 1. Coming to next week, it is the structural elements, measurements, and stereographic projection. So this week's the second week course is purely based on the geometrical aspect of different structural elements and their geometric representation and calculations. Then comes the very important part, is the concept of strain and deformation, followed by the concept of stress. And then when we will be knowing much about the strain and stress that governs the deformation processes, we will try to understand the rheology of materials and rocks as a whole. And by combining all these previous lectures, we will then come into the different kinds of deformation mechanisms of materials and rocks, starting from very micro scale to macro scale. Okay. And followed by foliations and lineation. These are very interesting structural observations that we see in the field. These are important structural features to understand the following things. Coming is the ductile deformation, For the first part of the ductile deformation, we'll generally talk about the mechanism of folding and superposition. And for the second part of ductile deformation, there will be boudinage and related structures. So foliation and lineation are the two important aspects of ductile deformation, or these are the signatures that tells us that ductile deformation has taken place in a region. And to understand the superposition of deformation, these features like foliation and lineation are very much important altogether to understand the general behavior of ductile deformation features that we observe in the field. Then comes the brittle deformation, like ductile deformation. Another part of, or another end of the spectrum of deformation is the brittle deformation, which includes fractures, joints, and faults. And altogether, then we will talk about the concept of ductile to brittle ductile shear zones, which is a very much important topic in the research aspects of uh, not only the research aspects of structural geology, but also for ore disposition and mining. And finally, the course will be concluded by the concept of lithostructural mapping. So this is the overall course outline. And following these particular topics in each and every week, we will discuss these things in our live interactive session. So the live interactive session will be held every week for the next 12 weeks. So today is the first live session, that is 27 July 2024, and this is the time of the live session, 4 p.m. to 6 p.m. evening, and live sessions on each Saturday at the same time. So this is the fixed time for each week's live session, and this is the session link. Anybody who has this link can feel free to join the course live session to gain some insights on structural geology. Now coming about today's live session. So in week one, the concepts that we learned is, or the concepts that we learned are the importance of this subject, that is the structural geology. I believe that Professor Mishra has already elaborated on this thing. And other than that, different aspects of structural geology, the importance of scale of observation, homogeneity and heterogeneity of geological structures, interpretation of information via geometric models, kinematic models, mechanical models, and numerical and analytical models. So this was the entire schedule for week one lectures. And based on that, what we will do in today's live session is to have an interaction about week one course content and answering doubts, if any. I will prefer to keep this doubt clearing session towards the end of this live session. Then comes solving conceptual questions related to the week one course contents, so that it will help you to solve your given assignments. Then I will summarize and conclude today's discussion by planning for the upcoming live session on the next week. Okay. Okay. So as I told that I will start today's discussion by solving conceptual questions related to the week one contents. So the idea is that I will show you questions. So I have prepared 10 questions. Sorry, is anybody trying to say anything? Hello. Okay. So as I was saying that today we will be, we will start today's discussion by solving questions. So the live session will go like this. I will prepare some questions. Like today I have prepared 10 different questions from the concepts regarding week 1. I will display the question and give you some time to figure out the answer by your own, and then we will discuss the different options given by, I mean, more detail or elaborate discussion on each of these questions, how to solve them, what is the logic behind the answer, and finally we will move on to the next question. So this is how I will be conducting this live session, so that it should become interactive. So I would like to request all of you who has joined this live session to please feel free to talk. So this is not an examination. This is not, I mean, there is no credit or discredit for attending the live session, right? So it is just for your own betterment, for the understanding of the subject. Please feel free to stop me anytime, anywhere, if you have any kind of doubt while solving the questions. And please try to interact with me. And you should also understand, I mean, you will be also able to understand that as I am not being able to see you, anyone, live, or I mean directly in front of me, so it is hard for me to tell whether everyone is getting what I am trying to say or convey. So if anyone is having any doubt, please stop me at that very moment and ask me to repeat. I will repeat as many times as you want. Okay. So without further anything, we should, I mean, start today's live session by solving different kinds of conceptual problems. So this is question number 1. So let's just say what is saying. Which one of the following option is correct? So there are 4 options given. The first option is a rock that is homogeneous at outcrop scale will always deform homogeneously at that scale. Option B, a rock that is heterogeneous at outcrop scale will always deform heterogeneously at that scale. Third option is that a rock that is isotropic at outcrop scale will neither deform homogeneously or heterogeneously. And option D is that the rock at outcrop scale can deform either or both homogeneously and heterogeneously. So this is the question. The main idea is to answer what will be the type of deformation, whether it will be heterogeneous or homogeneous in the outcrop scale. So I will give you 1 minute or 2 minutes to think about the question, and then we will solve it. So if you already got the answer, you should say, unmute yourself and say what is the answer.
Hello,
Yes, who
good
is
morning.
this?
Pawan, sir.
Yeah. Have you got the answer?
Yeah, according to me, this D option is correct.
Option D.
Yeah,
Okay. So and now would you like to elaborate that why do you think the option D will be correct?
it depends upon some homogeneity, heterogeneity, but it's mainly depends upon the type of stress, direction of stress, and the forces which is applicable on the rock. That is more important than this uh, composition part, or as is.
Exactly. Exactly. Thank you. You have got the correct answer. Very good. So as Pavan said, the option D is the correct answer. So if I just switch on to pen mode, yeah. So option D, this is the correct answer, and I will discuss That why is it the correct answer? So as told that the homogeneity or heterogeneity of deformation has actually nothing to do with the composition of the rock, right? So we will also learn these things in next different weeks, but I guess I can share some insights is that deformation deformation itself can be homogeneous and heterogeneous. How so? So the heterogeneity or homogeneity of deformation has nothing to do with the compositional or textural or mechanical homogeneity of or heterogeneity of rock. It is purely dependent on the type of deformation I am applying on the rock. For example, let me draw. This is, say, for example, an isotropic or homogeneous rock. Okay, isotropic and homogeneous rock. Now, this rock can undergo a very uniform deformation, like I can deform this rock in pure shear mode. So it will be a square will turn into a rectangle. So this is pure shear deformation. I can also deform the rock in simple shear, right? Where the square it will be deformed into a parallelogram. So these two deformations, these are homogeneous deformation. But I can also apply heterogeneous deformation. Heterogeneous deformation because it will consist of different modes of strain. Heterogeneous deformation will generally contain different modes of strain, right? So it can contain compression, tension or extension, and shearing. Altogether, this isotropic and homogeneous material, I can deform it like this. right? So then now no of the, I mean none of the regions in this rock will have similar deformation. Within the rock will have similar deformation. Okay, so in that case, if I observe one part of the outcrop and try to compare with another part, I may not find any similarity, or I can find similarity as well. So that will entirely depend on the stress regime, stress regime in which the rock is undergoing the deformation. So the important part is stress regime, right? For example, I can say is that during burial or diagenesis of a rock, most of the deformation that is being accommodated during that period is most likely to be homogeneous. But that will be true for any kind of rock, whether it is being anisotropic, isotropic, homogeneous, or having different kinds of composition as well. All of the materials will suffer equivalent amount of deformation because of the particular stress regime we are talking about. So that is a regional scale deformation. But then if I transfer to another location, say for example, a ductile shear zone within a subduction zone where a plate, an oceanic plate is being subducted within another plate, and at the mantle and the plate interface, we are having a very strong deformation. So in that case, the sense of asymmetry in the deformation will be very much higher compared to what we will be seeing in case of burial or diagenesis. The deformation in subduction interface will be highly localized, okay, and most definitely be heterogeneous because of the very large strain rate, very large strain deformation, and the heterogeneity of the rock as well as the stress patterns. So depending on the stress regime, that means in depending on the different tectonic, I mean tectonically significant areas, whether the region is tectonically stable or whether the region is tectonically unstable, all these kinds of things will ultimately control or govern how the stress is being applied on the rock. For just having the hydrostatic stress, I mean or the hydrostatic pressure without any kind of differential stress, a rock can even squeeze into a very denser form, but that kind of deformation will automatically be homogeneous. There will be no component of heterogeneity in that kind of deformation if we just simply apply the hydrostatic pressure. But instead of that, if we apply a deviatoric stress or a very high difference of stress from one part to the other part of the rock or any kind of object or material we are talking about of with a finite dimension, in that case a certain differences in stress and their direction of application as well as the rate of deformation, all these things will control whether the outcome will be heterogeneous or homogeneous. So for the one of the rule of thumb is that if we have to have a heterogeneous deformation, we should the deformation process should contain this thing, that is sub sub simple shearing, as well as non-coaxial deformation. So these are new terms, but I guess when we will be talking about the ductile deformation or the deformation mechanism, or even before that, when we will be talking about the strain and deformation, we will see what is coaxial deformation, what is non-coaxial deformation. So these kind of strain patterns and their associated stress will actually govern whether the outcome of the deformation will be homogeneous or heterogeneous. So to keep in mind, that is why I put this question at first. Homogeneity and heterogeneity can both occur independently, as in the composition of rock as well as in the type or the mode of deformation as well. So these two, I mean these two parts, these two homogeneity are not same. Homogeneity of rock will essentially talk about its mm, distribution of different elements or different minerals, whether they are localized or uniformly distributed overall in the rock mass or the volume of interest. That kind of homogeneity is essentially related to its composition or texture or overall characterization of the rock, but not its deformation behavior. Its deformation behavior will be dictated by in which geometric in which geometric orientation, or to be precisely, in which stress regime it is being deformed. Now that will create a very another dimension of homogeneity and heterogeneity, which shall not be associated with the compositional homogeneity or heterogeneity of the rock. So these two things are entirely different. One is the intrinsic property of the rock, that is the compositional homogeneity or heterogeneity, but the deformational homogeneity or heterogeneity, that has nothing to do with the composition, but entirely relies upon the stress regime in which the rock is being deformed. Okay, so that is the main take home message from this question, is that there can be different kinds of homogeneity and heterogeneity. It can either be in time as well, it can be on in the scale of composition of the rock, and also it can occur in the form of deformation. Structural geologists has to deal with every one of them. When we are going to the field, not only we observe compositional homogeneity or heterogeneity, we do also observe temporal homogeneity or heterogeneity, that is the emplacement and subsequent deformation and metamorphism and their superposition in different periods of time. So there is a temporal homogeneity, heterogeneity, there can be compositional heterogeneity, and there can be deformational heterogeneity. Our job as a structural geologist is to untangle all these different phenomena and link them linearly to create a scientifically valid story or hypothesis about the deformation mechanism or the deformation process of a region. That is our job. Okay, I guess so. Anyone has any doubt on this question? So please feel free to ask. So if not, then I will move on to the next question. Okay, so the next question is, four geological events are provided. Number one is the subduction of an oceanic crust. Number two is fissure volcanism at Hawaii. Number 3 is mantle convection cycle. Number 4 is the deformation during impact cratering. Arrange the above mentioned events in the increasing order of their time scale. Option A is 2, 1, 4, 3. Option B 1, 2, 3, 4. Option C 4, 2, 1, 3. And option D 4, 3, 2, 1. Just like the before, I will pause for a minute, let you try to answer the question, and then I will talk about what is the right answer. Okay, so any answer? Yeah, if you can just speak directly. Okay, so you don't have to raise your hands. You can just unmute yourself and talk.
Um, in my hello,
C,
C,
in my
C,
opinion, C, sir.
C is right.
Okay,
C
so
is
Pavan
correct one.
and Danish both are saying that option C is correct, and they are rightly to say so. Option C is definitely the correct answer, and I will give you the explanation behind that. So, as in the previous question, I was talking about heterogeneity in time scale, right? So, geological processes do occur in different times, right? So, in this case, first of all, discuss what is the fourth option. Fourth option is definitely deformation during impact cratering. Option 2 is the fissure volcanism at Hawaii. Option sorry, option 1 is the subduction of an oceanic crust, and option 3 is mantle convection cycle. So now to give you the frame of time, impact cratering, sorry, so okay, so impact cratering occurs less than 1 second. It can also occur within a millisecond. So this is the duration we are talking about, right? Now the second is fissure volcanism. Fissure volcanism generally takes 1 day to 1 month. So think about the time scale. This is 1 second. I can say 1 second. 1 day to 1 month means 3 into 10 to the power 3 second to, now you can say 1 month is how much second in the order of 10 to the power something. So it is generally 1 day means sorry, 1 day is not this. I'm sorry. This is 1 hour. So let us just convert these things into seconds. That is the unit of time in physics or any kind of scientific calculation. We use seconds as the unit of time. So 1 day means how much second? One day means 24 hours. Each hour has 3600 seconds. That means 3600 times 24. That means if I calculate in my calculator, so it is,
8.64 into 10 to the power of 4 seconds.
yes. So roughly 8.6 times 10 to the power 4. Now if I just multiply it with 30, this will be for a month. So in the order of 2.5 into 10 to the power 8 second, right? So this is the power we are, I mean 10 power we are talking about. Now this is impact cratering, fissure volcanism, then comes subduction of an oceanic crust. Subduction of an oceanic crust generally, I mean, if I even consider that the rate of subduction is few millimeters a year, right? For a visible amount of subduction, we have to wait for at least 1 year. I mean, not visible, measurable amount of uh, subduction taking place. So minimum is, so I can write it like this. So it is greater than 1 year, right? So 1 year is how much second? So it is in the order of right, 3.1 into 10 to the power 10 seconds almost, right? In this order, right? No, I guess it is 10 to the power 9. So this is the dimension. And for,
Sir, you mentioned wrong the 1 day to
yeah,
1 month, 2.5 into 10 to the power of 6, sir.
2.5 in 10 to the power 6, right?
Yes, sir.
Okay. Okay. And for mantle convection, the time scale is at least 100 million years. So that means just multiply this with 10 to the power 8, right? So in the order of 10 to the power um, 17 to 18 seconds. So this is the time frame that we're talking about. So can you name any other event that is as quick as impact cratering and affects the overall deformation of our planet?
So earthquakes.
Exactly, earthquake. So you can see that all of these things have their own importance, like impact cratering and earthquake. Those are as important as mantle convection, because if there wasn't impact cratering, you know that the Chicxulub crater that has been found near the Mexico, that crater was believed to be the largest crater ever appeared on planet Earth, and that was responsible for the destruction or extinction of the dinosaurs, right? In the end of the Cretaceous period, the KT boundary that we talk about, that was solely because of an impact cratering. So imagine that particular event occurred within a second, just within a second, and it destroyed an entire species and also many other life form from the earth, and provoked or facilitate the Deccan volcanism and other tectonic processes just within a second. And so is the earthquake. All the major earthquakes, the tsunamis, all these things, they also even occur within seconds. The huge amount of elastic energy is being released within just seconds, and destruction is inevitable. And it permanently changes the form of tectonics. At the plate interface, as we are seeing from now. But apart from those, earth is slowly evolving. Subduction is important. So the Pacific Ocean that we are seeing, the Pacific plate currently we are seeing, it will be no longer there in the coming 200 million years. It will all be destructed or consumed within the mantle itself, and then again a new plate will be generated at the same from the perhaps from the same ridge or from a different mid-oceanic ridge. It will come up and create another plate, and that the creation of this plate, the destruction, this is all controlled by the mantle convection. So mantle convection occurs in the range of 100 million years or so. And there is another important, even what can I say, it is also from a very, even for a large duration of time, that is the rotation of the inner core of the earth. It perhaps be the slowest process that we are observing inside our earth. So there are different time periods of events. So there is certain heterogeneity in temporal, there is certain temporal heterogeneity as well, that I was trying to say. Now the thing is that the interesting part.
Sir, uh,
Yeah.
the rotation of Earth is coinciding with the change in magnetic north. It can also said in this way.
Rotation of earth, the rotation of the core.
Yeah, but core.
Yeah, of course, the rotation of the inner core is definitely related to the geodynamo that is being created, and that is affecting the uh, polarity reversal of the magnetic field. It is also an important issue. I encourage you to all look into the fact that there is a particular frequency or a time period of this temporal, this polarity reversal. So the motion of the inner core changes in a certain frequency or a time period, over which the magnetic field of our earth is also changing, and that is being reflected on the magnetic anomalies that we see on the sea floor, right? The spreading ridges of the sea floor, they record these signatures of these magnetic reversals, and from that we are being able to determine the age of the oceanic plate that is being subducted or being created, right, in a cycle. So what I was trying to convey is that this heterogeneity there can also exist a heterogeneity in time. So now, just a philosophical point of view, which event would you like to say is heterogeneous in each of these events? Which event is heterogeneous and which event is homogeneous with respect to time? Can anyone answer the question?
Sir, impact catering is heterogeneous.
Exactly. And why so?
Such a intense stress regime is formed at that time. Some portion has in the ductile has been given in the ductile zone, some has brittle deformation, and some has even changed their ash form has created, and numerous rock forms has formed in this impact cratering zone.
Yeah, you're absolutely correct. And I appreciate the answer. It is definitely the impact cratering that is heterogeneous. But I was also saying that apart from the heterogeneity in deformation, can you say that heterogeneity in time, such as impact cratering, is heterogeneous with respect to time because of its randomness? We don't even see impact cratering in a particular frequency. It's a random thing, right? We don't know what was the last impact cratering occurred, and we also don't even know that what will be the next impact cratering. And so as the earthquake, we don't know actually how to predict. We all know the tectonics, how it works. We are also developing a strong idea about the frictional properties at the earthquake interface, but we still don't know, and we still don't can't predict whether there will be an earthquake is not I mean an earthquake is going to occur or not. But volcanism is pretty much consistent process. Once it starts to flow in an uniform pattern, and it continues to follow the same path. I mean, we all know that where the fissure eruptions can occur, we know the locations. There is a geographic certainty as well as a temporal certainty. That means it will at least continue for some days to months, we know that. Similarly, subduction is also a very much stable process. It is continuing, right? There is no stopping, there is no going back. It is a permanent process, cyclic process that is continuously going on. There is no break in the process, right? And even if there is a break in the process, it is within millions of years of range. And so does the mantle convection. It is also a process that is continuously happening, and there is no break in its continuity, right? The reason I'm telling this is that the temporal heterogeneity is also important for a structural geologist, because when we will be conducting some lithostructural mapping, you will encounter different kinds of unconformities. So unconformity is such a thing that tells that there is there was a temporal discontinuity of an event, whatever that might be, and was that is being recorded as a hiatus within the rock record or in the outcrop that we're seeing. So deformational heterogeneity, compositional heterogeneity, as well as temporal heterogeneity is also important for understanding the duration of the process, what stopped it, then how it uh, I mean continued again, how it started again. Okay, so all these kind of things are and informations are extracted from observing the rocks in the field only. So apart from, surely there was some mention of the scale and heterogeneity of composition and deformation in the lecture. I I tried to emphasize on the temporal heterogeneity of the rocks. The geological processes. Okay. So now the next question number 3. It says, following are the uh, hand specimen following are the hand specimen images of A, banded iron formation, and B, migmatite gneiss. Okay, so these are photographs from Google. A is banded iron formation, BIF. BIF is commonly known as the source for iron, and the other one is migmatite gneiss, which is a metamorphic rock. Now choose the correct option. A and B both are heterogeneous in microscopic and macroscopic scale. B, A is homogeneous in microscopic scale, B is heterogeneous in microscopic scale. C, A and B are isotropic in macroscopic scale but anisotropic in microscopic scale. Option D, A and B both are anisotropic in macroscopic scale but heterogeneous in microscopic scale. Okay, so choose wisely. There is only a correct answer. All these all these options are closely related to each other, but if you can think logically, there will be only one correct answer. So I will give you another minute, pause, and let think about the question and think about the answer.
Uh,
Yeah,
Hello.
yeah.
In my opinion, is answer A is correct.
Okay. In your opinion, option A is that which is A and B both are heterogeneous in microscopic and macroscopic scale. I beg to differ with the answer, but yeah, I surely this can be an option. But I will let you think once more. Uh, let's see.
Yes, sir, sir. Both are
Option
heterogeneous
B,
in
sir.
microscopic. A option is correct, sir, in my opinion.
Okay, Danish is saying that option B is correct, and who said
A, sir.
again? Option A
B,
is
sir.
correct.
Yes.
Who is saying option B?
Sir, Ishwari.
Okay, so you are telling that option B is correct. A is homogeneous in microscopic scale, and B is heterogeneous in microscopic scale. So I would like to also say that B is the correct option. Could you please like tell why you thought that B is the correct option?
Sir, B is heterogeneous because gneiss it contains feldspath and other minerals also, sir. So it is so heterogeneous.
Okay, yeah, I get that you are going in the right direction, but uh, yes, I mean your answer is right, and you have rightly pointed out I mean the point. So let me elaborate on that. So she thought that option B is correct, and I agree with her. And the reason behind is that we are observing in microscopic scale, right? Now, for observing microscopic scale, what you will do? I mean, what will you do? You will prepare a thin section or a slide. Now, say this rock, say for example, this is 10 centimeter. Okay, so this is roughly the scale of a hind specimen sample. Both have both of them has the same scale, right? 10 centimeter. Now from the 10 centimeter region, you will only prepare thin section of this or thin section of this. I mean, if you are preparing slides at once, you cannot prepare the entire section. I mean, this preparing a slide is not possible for this entire section. For a microscopic view means 10 to 100 micron range. In this range, if you observe something, that will definitely fall either on either of these bands, right? These bands itself are pretty much thicker than 100 micron. So even if you're trying to prepare a thin section, it will generally fall either of within this kind of structure. So microscopically, so if I observe this portion in microscope, so it will seem to have homogeneous material, because this is I mean iron, right? And this region, if I observe this in microscope, it is some oxides, right? This is chart silicon oxide, and it is cryptocrystalline. So this is pretty much homogeneous even in microscopic scale. Macroscopic scale, it is also homogeneous, this part, and for microscopic scale also it will remain homogeneous as well. But coming to gneiss, as she pointed out, that this is a crystalline rock. So say for example, I am trying to prepare a thin section from this region. Even if I prepare a thin section from this region, I will see different kinds of minerals associated here. There will be quartz, there will be K feldspar, there will be mica such as biotite, there can be even some pyroxene, right? So this is a migmatic gneiss. So this is granite or gneiss. Of course there will be some I mean mafic as well as felsic minerals. So all those things there will be there in even in mineralogical scale, I mean sorry, microscopic scale. So this rock, this is in macroscopic scale. Macroscopic scale, it is heterogeneous and anisotropic, right? But in microscopic scale, it is only heterogeneous. We will not be able to see whether the rock is isotropic or anisotropic in thin section scale or microscopic scale, but we can definitely figure out that okay, so this is quartz and this is feldspar, this is biotite, this is muscovite, this is pyroxene, all kinds of things. So this is so in thin section scale, migmatic gneiss will definitely be heterogeneous, but the BIF will remain homogeneous, because the scale itself will not allow to see the entire section of the rock. That is why banded iron formation will remain homogeneous in thin section scale. Now, those who have answered, like Pavan, Danish, they have answered option A is also, I mean, correct according to them. So what is option A is saying? A and B both are heterogeneous in microscopic and macroscopic scale. Now, the heterogeneity in microscopic scale, that can even occur from one part to another as well. If you compare, so if I see this part, so if I compare the red portion, thin section of this red portion with the thin section of this black portion, of course it will be different. But within these individual sections, we will not see a pretty, I mean there can't be a big difference in their, I mean homogeneity, right? But if you compare the black layers, thin section of the black layers with the thin section of the red layers, then this comparison itself brings out to another scale. Then this comparison no longer stays in the micro scale, it is automatically being transferred to the macroscopic scale, because you, I mean the two region that you are comparing, they both are lying at least some millimeter apart. So it is automatically being transited from the microscopic scale to the macroscopic scale, right? So the compositional heterogeneity will prevail in migmatic gneiss.
Sir,
So this was, yeah,
yeah,
go on.
just a question for macroscopic level.
I
I
am
think,
sorry, Pavan, I can't.
hello.
Yeah, yeah, yeah. Now it's
Uh,
clear.
uh,
Yeah.
is in the banded iron BIO?
Yeah.
in the specimen, it
Yeah.
is a heterogeneous rock. It's not homogeneous rock.
Yes.
Macroscopic. Yeah.
Yeah.
It's a
Macroscopic scale, it is heterogeneous. Yes.
and even if we prepare slides in even if we prepare slide for cryptocrystalline rock, there are number of oolitic structures, some number of different structures are seen under slide there.
Yes, I understand, but that will be a case important for limestones specifically that you are talking about, different kind of bioorganic structures and some kind of inorganic deposits. But whenever you're talking about these kind of charty rocks charts, say for example you took chart from the BIF, that is a red layer, and you took shale, another sedimentary rock or mudstone. Now shale, do you think that shale is heterogeneous in macroscopic scale?
Macroscopic, no, it's not heterogeneous, it's homogeneous.
Yes. No, sorry. Macroscopic scale mean I'm talking about hand specimen scale,
Yeah,
right?
and
Hand specimen scale, shale seems to be heterogeneous
uniform.
because of the layerings, right?
Yeah,
But if you prepare a thin section of shale, I'm pretty sure that because of its very, very fine grain, you can't even identify even individual minerals from there. You have to do, I mean, you can, of course, identify using the scanning
FR.
electron microscopes,
Okay.
but in conventional optical microscopes, it is very difficult to differentiate between whether that is a quartz or that is a mica or even it's a feldspar or not. So these kind in this kind of scales, that means if you also see from a range of 10 to 100 microns, the grain sizes of these I mean minerals in shale or mudstone or chart, they're below that. So microscopic scale means for optical microscopic observation, we generally follow the range 10 to 100 microns. So anything having a grain size below 10 micron will automatically appear as homogeneous even in that scale. So then we have to dive into higher magnification through uh, scanning electron microscopy or some kind of other analytical I mean methods like EPMA or so,
Yeah.
where we can even see some nanometers to micrometers range of scale. So entire observation will also then shift from microscopic scale to nanoscopic scale. In that scale, again, it will be heterogeneous.
High heterogeneous.
Yeah. So that is the concept.
Okay.
Yeah. Thank you. Okay. So the next question, this is an interesting question. Which of the following options is correct? Option A, brittle deformation followed by ductile deformation. Overall structure is continuous. Option B, brittle deformation followed by ductile deformation. Overall structure is discontinuous. Option C is that ductile deformation followed by brittle deformation. Overall structure is discontinuous. And the final option is ductile deformation followed by brittle deformation. Overall structure is continuous. So the objective is to see this image and then interpret the answer, what it should be.
Answer C, sir. Answer is C, sir.
Sorry, Pavan, I can't hear you.
Answer C, sir.
Answer C, ductile deformation followed by brittle
Better
deformation.
deformation and
Overall
discontinuous.
structure is discontinuous. Exactly. So this is the correct answer. So why do you think that ductile deformation is followed by brittle deformation and not the other way?
Because brittle deformation, some dike has been cut across this earlier fold, recumbent fold.
Exactly. Exactly. So the relationship is in stratigraphy that we call the principle of superposition, right? So the answer is generally observing through the cross-cutting relationship. Now, the enigma is not an enigma. A proposition is that why do you think that the dike cross-cutted the fold and not the fold cross-cutted the dike, right?
There is some displacement in fold. Displacement is there.
I'm sorry, Pavan. Can you please the mic closer to yeah.
Some displacement is there, sir, in, in your figure. I
Um,
think it seems that there is some displacement.
yeah, there
So,
might be some displacement. Yeah.
so
Uh,
for a dike to occur, it need a structure. That is, it need a basement through which it needs to flow. So a dike is always on a fold structure.
okay. So you think that for flowing from one direction to other, the magma that is being flowing, it already needs a stable structure to flow. That's also correct. And as Pavan told that there is some displacement, faulting observed within the fold. That is also correct. But you all missed one very important point. Now, just let me show some diagram. Say, for example, this is my bedding planes, right? Bedding planes. That means these are compositional layers or primary layers or primary structures, right? Now, within this, a dike has intruded. So, intrusion of dike takes place. After that, once the intrusion is complete, I am folding this entire packet of structures all together. What will happen? The outcome will look like this. The final structure will look pretty much like this. That means in that case, the dike
Yes, dike is folded.
would also have been folded, right?
Yeah, yeah. Yes.
That is the main interpretation of cross-cutting relationship of structures. So if the dike intruded earlier to the fold, episode of folding, so the bedding planes and the dike altogether would have folded, right? But instead, we are seeing that the fold has taken place, and after that, the intrusion of dike has occurred. And the intrusion does, the intrusion did not affect the structure, internal structure of the dike. That means, since the dike is intact, that is the proof of the cross-cutting relationship. So, in order to examine the principle of superposition that is important for stratigraphy as well as mapping in structural geology, you should always try to find which lithological unit has remained intact. That indicates that that unit, those units which did not undergo any kind of deformation is the latest, followed by subsequent, I mean, uh, not followed by, it is prevailed by subsequent deformations that took place earlier, and the final stage should be the litho unit that is intact. So, for principle of superposition, the relative degree of deformation is also important. if we had observed that the dike itself, now for this dike, for example, in this dike, not this color, let me change it. For example, this dike, if we observed very high degree of metamorphism in this dike, what could be the interpretation? The interpretation would be like this, that initial structure was the folding, which was followed by brittle deformation, which was again perturbed or altered by some kind of fluid activity that changed or altered the composition of the dike, but did not affect the uh, folded structures. I mean the composition of the folded layers. So in that case, the sequence of events would be folding, then brittle deformation, and then fluid related alteration or metasomatism, right? So for finding the signatures of deformation, you do not always have to have structures. That is the important part. Like if you go to the field, I'm sure that if anyone has conducted any kind of field work till now, the field experience will tell them that it is very rare to see structures like this. Very often you will encounter no structures in the field. What you will get, different kinds of rock, or even for a same kind of rock having different kinds of degree of metamorphism, and based on that you interpret that, okay, so whether there is high degree of deformation or low intensity of so the intensity of deformation is often dictated by the degree of metamorphism that we observe in the field. So that is very important to understand. These kind of structures, they are all pretty good to observe in textbook, but whether you're whenever you're going to the field, observing a structure, it is very rare and difficult. Your teachers would tell you that, okay, we are going to do a field work in this region, it is deformed in several episodes, there might be 3 to 4 stages of deformation, there is folding, there is faulting, diking, intrusion, whatever, all kinds of structure may be present there. But all these things will be in a regional scale. Very often or very rarely you will encounter such things as this kind of structure that is presented in this picture. But your task is to correlate the compositional heterogeneity in a particular direction of your fieldwork with structural attitudes that we will discuss in the next week, with the different kinds of rock types and their changing degree of metamorphism. All the information put together, you prepare a geological map from which you try to infer what could be the possible overall, the regional structure that has undergone the deformation. So structural geology alone cannot help you to understand the entire processes the region has suffered. You should always need the adequate amount of knowledge of igneous petrology, metamorphic petrology, sedimentology, and in sometimes even paleontology as well, right? So structural geology is not a, sensu stricto, a very restricted subject. It is a very broad subject, and it has all kinds of information available. You just have to play with them to actually get to the actual scientific content. Okay, this next question is pretty much easy, and it says that GPS stations are installed at various locations and elevations along the entire length of Himalayas to track the rate of upliftment of the mountain and the motion of the Indian plate. What kind of structural analysis are involved in the process? Option A, geometric analysis only. Option B, geometric, kinematic and mechanical analysis. Option C, geometric and kinematic analysis. And option D is numerical analysis. What do you think will be the right answer?
What is this mechanical analysis?
Sorry, Pavan, I can't hear you again.
What is this mechanical analysis?
Mechanical analysis, as you I'm sure that you have seen the lectures. So in lecture 2, I guess, there was mechanical modeling. Mechanical analysis means mechanical modeling that involves the uh, experimental investigation of the strength of different kinds of rocks and the rheologies and their flow mechanisms, all those things. So that is the mechanical analysis.
In my opinion, it's a C.
Yeah, it's exactly correct answer, option C. And why do you think it is C?
It's C because geometric elevation we have studying, and the moment of plate we are studying out rate of the movement of the plate. That is kinematic analysis we are doing
Exactly,
simultaneously.
exactly. So if I see that, so this is, pardon me for drawing a very bad map of India, but I guess you get the idea. Is that, so this is the belt of Himalayas, as we know, right? And we have put the GPS stations in different locations, right? Along each and every elevations and different locations of Himalayas. Now, what does the GPS do? Now they measure, say for example, for a period of 5 to 10 years, right? So the recent GPS track. So what will happen is that since the plate is moving, the Indian plate is moving under the
Well,
Eurasian plate, right? So that is the theory for the formation of Himalayas, right? So since the plate is moving, the Indian plate is going forward, towards the north, and that is why all the GPS station will move along there, along that path in certain direction. Now the finding is very much interesting. I urge you to see this finding in internet. I may also would like to share some papers related to that. You can go through those things. So the observation is that the scientists estimated that the path should go linearly like this, right? They thought the path would be straight line. Since this is moving forward, it is pretty straightforward to estimate that all the GPS locations should be moving along this direction. Instead, the surprising finding is that the recent GPS locations are showing a path like this of various magnitudes. So Himalaya is actually rotating. So if you can see, there is a rotational motion involved. So this is the recent GPS signals for the past 10 to 20 years. We collected the data and we see India is not actually going straight, but it is actually rotating. Rather, to say that it is pivoting somewhere around here. So this is the center of this circular motion, and the plate is moving just like this. You know this point. So this is the pivot, recent pivot along which the Indian plate is moving like this, and this point here, it is north of north of Sikkim, and it's towards this east, ekdam farthest east point of India. There is China here, China India border, this location. This is Namche Barwa. It is of course lying on the Himalayan range, but this is acting as a pivot. So this the Indian plate is basically pivoting around this point, and that is why This is the fastest growing mountain point on the world. We all know that the height of the Himalaya is continuously growing, and that is being determined from the geometric and kinematic analysis only. So what is the geometric component in this analysis? This finding that the path is curved is the geometric analysis. So I can write it like this. Number one is finding the path, right? This is curvilinear path, and this is coming from the geometric analysis, right? And the magnitude of displacement through which we are calculating the strain, that is the kinematic analysis. Okay, so I urge you to see this Namche Barwa. It is very interesting to find that the Indian plate is actually rotating, not going forward. Okay, the next question is that this is also a very interesting question. How igneous petrology and structural geology are linked in understanding the volcanic topography and geomorphology? Option A, by knowing the composition of the lava, its viscosity and rheology. Option B, by knowing the eruptive style and composition of the lava only. Option C, by knowing the deformation behavior and eruptive style only. And option D is none of the above. So think for a minute, then answer correctly.
So what is the meaning of rheology?
Rheology means we will of course learn in the coming week, but let me mention you in details. So the term rheology means basically response, I mean mechanical response of a rock, mechanical response of a material when subjected to external stress. So this is another branch of subject which tells that basically deals with the response, mechanical response of a material when it is being I mean when we are trying to deform it. For example, you have a flour dough, ठीक है, आटा जिससे आप लोग रोटी बनाते हैं. So you take atta and you knead it and you make a dough, right? So you have this flour dough, atta dough, and then you hold it like this. So eventually you'll see that the slowly the dough will start dripping, right? So under the influence of gravity, this dough, which is apparently solid, you can say, it will flow with respect to time. You see that it will slowly come, it will slowly extending like this, and it will eventually fall. That is the rheology, because that is the response of the material under the influence of stress. In this case, the gravity is acting like the stress. Now if you have a glass, uh, sorry Pavan, you are trying to say something.
Yeah, it's answer A.
Okay, You answer, yes, I'm coming to the answer, but just let me finish what you was telling that. So I told you about the flower dough and how it is behaving, but in that similar case, if you hold a glass, okay, the glass won't fall like that, right? Because it is not flowing under the influence of gravity, because it is stronger. So that is rheology, to estimate that how much strong a material is with respect to the applied stress and time, right? So Pavan told the answer is, it is A. It is correct answer. Is that uh, so the answer is A, because it is by knowing the composition of the lava, its viscosity and rheology. So I assume that you guys all have an idea about viscosity. What is viscosity? Viscosity,
Is the frictional force between the
Movement
two
of
layers.
yeah. So very simply speaking, it is the resistance to flow, right? So how composition, so how viscosity is related to rheology? Viscosity and rheology.
If
So the answer is high
so
viscosity. High viscosity will generally mean high strength of the rock, right? Yes, Shwari, you are telling something.
no sir.
Okay, so viscosity and rheology are related like this. High viscosity means it will not flow under the influence of stress, right? As Pavan tell that there will be very much high frictional resistance within the layers, and it will not flow. So something which is not flowing, that means rheologically it has a higher strength, right? So this is how viscosity and rheology are connected, and these are the parts of deformation and structural geology. Now what about the composition part? So composition means, generally in this case, the silica content of the lava, right? We all know that high silica content, that means felsic lava, it will have high viscosity, and low silica content, which means mafic lava, it generally has a very low viscosity, right? Now high viscosity will prevent the material to flow. So in that case, high viscosity will create fissure, sorry, I mean stratovolcanoes, right? You all know about stratovolcanoes, which are very steeply sloping volcanoes having a crater above them, and these kind of stratovolcanoes are very much highly eruptive volcanoes, and that is because of this high viscosity of the lava, right? High viscosity of lava means felsic lava, which means rhyolitic lava. So generally rhyolitic lava. And low viscosity means fissure eruptions, right? Just like in Hawaii. And fissure eruptions generally involve basaltic lava. So you see, this is how this is how igneous petrology is related to structural geology. So to understand the topography, we need to understand the viscosity of the material and its rheology. If it is highly viscous, the rule of thumb is that it will explode in a very furious way. It will generally create a very highly steeping mountains, volcanic mountains, and the topography will be rough. So this is the geomorphologic manifestation of the process. And the high viscosity will occur because of its high silica content. That means the composition of the lava is rhyolitic. That comes from the igneous petrology knowledge. Similarly, for low viscosity lava, since the viscosity is low, the resistance is low, the strength of the rock is pretty low. So that means it will flow easily on the surface without creating such high mountains. So the topography and the geomorphology will be relatively flat. Okay, and then the composition that is linked is generally the basaltic lava. Again, the igneous petrology part. So this is how I guess you can relate one subject to another. So this is just a glimpse how you can relate structural geology with igneous petrology, right? Okay. Next question. This is an intuitive question. In which of the following litho units would you expect to see a nice fold structure in outcrop scale? Option A, granite. Option B, basalt. Intercalated shale limestone layers. Option D, quartzite.
C.
Yes,
C.
exactly. Option C. So to create a fold, we need softer lithology compared to its surrounding rock. You will of course learn in the upcoming lectures, but I just give you the glimpse of this thing. This is commonly known as the this softer lithology compared to the surrounding rock. This thing is termed as competency contrast, right? So high competent rock means it is very much stiff, or you can also say in I mean in simpler terms is the stiffness contrast. So it is very much easy to interpret like that. You have a layer of shale and limestone, these are soft rocks, and then again you have a granite which is a very hard rock. So which one will be stiffer? Of course the granite will be stiffer. Now if you're trying to fold it through some mechanism, what will happen? The granite and all these rocks like granite, basalt, quartzite, these being the stiffer rocks, they would break. That means since they have a very high stiffness, they will tend to break apart, showing the signatures of brittle deformations through fracturing. But probably the intercalated shale limestone layers, because they are softer, they would probably be folded without any kind of fracturing, since they have a very low competency contrast. So this is how you should learn in the upcoming lectures, that competency contrast or the stiffness contrast between different layers actually controls their ability to fold and manifest in different scale of folding, right? Okay. Now there is a numerical question. Two rock units P and Q are undergoing deformation at a depth of 5 km beneath the continental crust and oceanic crust respectively. Calculate the difference between the confining pressure experienced by Q and P. Consider the densities of continental crust and oceanic crust being 2600 kg per meter cube and 2900 kg per meter cube respectively. So whenever we are saying that this is the surface and I have a rock mass or any object kept in a depth of h, so the overlying material, so if the overlying material has a density of rho, then the hydrostatic pressure P will be calculated through the formula H rho G. I believe that many of you know this formula already. G is gravitational constant, basically gravity. You can consider for this problem as approximately 10 meter per second square. Okay. So for pressure beneath the oceanic plate, the formula will be, the calculations will be 5 kilometers means 5000 meters, right? Times the density is 2900 times 10, and the pressure beneath the continental crust will be 5000 times 2600 times 10, right? So the difference in del P, that is the difference in pressure, that is POC minus PCC. So if you take common the 5000 times 10 part, you will get the difference. That means 5000 times 10 times 300, right? This much Pascal, or 15 into 10 to the power 6 Pascal. 10 to the power 6 Pascal means 1 megapascal, right? So the difference will be 15 megapascal. Yes, anybody who wants to speak, please feel free to. I mean, you don't need to raise your hand. You can just,
Sir,
yeah, yeah. Please continue.
सर जो कॉन्टिनेंटल एंड ओशनिक क्रस्ट के नीचे लिखा है कि बेनीथ द कॉन्टिनेंटल क्रस्ट एंड ओशनिक क्रस्ट, तो उसमें हम कॉन्टिनेंटल क्रस्ट का थिकनेस एज ए फैक्टर लेंगे कि नहीं लेंगे, या फिर
Uh,
ओशनिक क्रस्ट का थिकनेस एज ए फैक्टर लेंगे कि नहीं लेंगे?
इसमें अगर वो मतलब इसमें डेप्थ ऑलरेडी दे चुका है कि 5 किलोमीटर बीनीथ द कॉन्टिनेंटल क्रस्ट, मतलब सरफेस से, मतलब कॉन्टिनेंटल क्रस्ट का सरफेस से 5 किलोमीटर बीनीथ में, और ओशनिक क्रस्ट का सरफेस से 5 किलोमीटर डेप्थ में। तो ऐसे करके ये दिया गया है। नाउ इफ द क्वेश्चन सेज लाइक दैट कि तुम, आपको अगर ये कंसीडर करना होता है कि आप टोटल कॉन्टिनेंटल क्रस्ट का थिकनेस कंसीडर करेंगे या फिर टोटल ओशनिक क्रस्ट का थिकनेस कंसीडर करेंगे, in that case the question would have mentioned to consider, if the information was not given, then it would have mentioned to consider the average thickness of continental crust or oceanic crust, right? Because you know that the thickness varies largely in different places. Like in Cretan, the thickness is higher for continental crust. For a spreading ridge, the oceanic crust has a very minimum thickness. Just before the subduction zone, the thickness increases. So all kind of things can happen. So that is why, when if the question comes like this, that you have to consider the thickness of the continental crust and the oceanic crust, in that case the question should specifically mention to consider the average thickness. So the average thickness for oceanic crust is 5 kilometers, and the average thickness for the continental crust is 35 kilometers, right? So this average thickness, which is 35 kilometer and which is 5 kilometer, I hope you know that this configuration is being calculated using the concept of isostasy. So we don't actually know that what, where the, I mean the, where the limit is lying, but we calculate an overall estimation of the average thickness based on the isostasy of the mountains and the glaciers and all kinds of different structures, geodynamic scale structures. So as again, if nothing mentioned, then you simply calculate from the surface to 5 kilometer depths. And if they are specifically mentioning to consider the thickness of the crust as well, then they should mention that whether you should take the average thickness or they should specify what thickness they want to calculate. Okay.
ठीक है सर, ओके।
Okay. Okay. So next question is, distinguish the regions of dominant ductile and brittle deformation. So this is the picture given. This is not an MCQ, just a quick exercise um where you can see ductile deformation and where you can see brittle deformation. So of course, options you can see, like bend fault, slow slip events, mega thrust. These features are the signatures of brittle deformation. Why? Because all these terms are related to earthquake mechanisms, right? So this is the overall schematic representation of a general subduction of an oceanic plate, right? So this is the oceanic crust and this is the oceanic plate. So an oceanic plate is comprised of the crust and the part of the mantle. Together it is called the lithosphere, right? So a plate is always a lithospheric plate, not a crustal plate. Crust solely cannot be a plate. Plate should always consider part of the upper mantle along with the crust that contains, I mean, that creates the lithosphere. Now, the bend fault, slow slip regions, and mega thrust, all these things are brittle deformation because they create fractures. Unless there is a fracture, the energy through earthquake cannot release. So that is why wherever there is a fracture, that means discontinuity is taking place, and that means that the feature is essentially brittle. So these are the regions of brittle deformation. So where is the ductile deformation? Of course, asthenosphere, the lower part of the mantle, the four arc region, the volcanic arc region. These regions, I mean this part, these are the ductile deformations regions of ductile deformation. One interesting thing is to note that these regions are these regions suffer ductile deformation because of higher temperature. Of course, temperature is a controlling factor to manifest whether a material will deform ductily. I mean, whether it will show ductility or whether it will show brittle signatures, right? So I urge you to see these kind of general schematics of subduction zones and earthquake mechanisms, so that you can have you can, I mean, create a better understanding in a global scale or a regional scale how different how materials will show ductile deformation and how materials will show brittle deformation. So ductile deformation in general means deformation without discontinuity. Sorry, we yes, deformation without discontinuity. Brittle deformation means deformation with discontinuity, right? So that is the simplest differentiation between these two kinds of deformation. So in a subduction zone, generally, if there is some discontinuity taking place, most likely that it will eventually contribute to earthquake. So that is why understanding brittle deformation as well as ductile deformation both are important for us to eventually understand or grasp the mechanisms of this complex subduction dynamics. Okay, so the last question: match the following rocks with their appropriate conditions of deformation. So this might require a bit of knowledge about metamorphic petrology, because you know that metamorphic facies is nothing but the role of pressure and temperature on the chemical and mechanical behavior of rocks at different conditions, right? So eventually the minerals that are forming due to metamorphism will obviously be a signature of the conditions they were originated through, right? The pressure and temperature specifically. So that is why pressure and temperature not only plays an important role for metamorphism, it also plays an important role for how, I mean, what kind of deformation signatures we are going to see. So can anyone answer what is I mean, what is the right option for this table?
B, B, B,
Option
B, Bombay.
option okay, option B. Let's say option B means P1. That means mica cyst, low temperature and low pressure deformation. Very good. Mica cyst generally forms in a very low temperature and low pressure regime. Generally, in terms of metamorphism, this is green schist, right? Green schist facies. Okay. Q, quartzite. Again, a rock that forms from green schist to amphibolite facies. That means it should require moderate temperature, moderate pressure. So Q will be 4, right? Then comes migmatite. Migmatite is a kind of rock that is formed in, I'm sorry, I've written it wrong, in wrong location, I guess. This will be in this part. green schist to amphibolite facies. Okay. Migmatite generally occurs in the
Latotite.
granulite facies terrain, granulite facies, which is very high temperature to high pressure deformation. So R will be 3. This is very high temperature and high pressure deformation, granulate facies. And the remaining is, of course, blue schist facies, which has a very high temperature and very high pressure deformation. Generally, we see the blue schist facies in subduction zone. Subduction zone rocks generally display this kind of blue schist facies. So, of course, the correct option is B. So, the take home message from this table is that you should simultaneously study metamorphic petrology, igneous petrology, and sedimentology as well to get a grasp on the proper understanding of structural geology. Without the knowledge of composition, texture, their classification, and mode of occurrence, you cannot actually interpret the structures as well. You can surely learn about the different deformation mechanisms, but if you don't have the rest of the knowledge about the geology, the knowledge you will be gaining about the deformation mechanism will solely be based on the material science perspective. To incorporate the knowledge of the deformation of materials into the geological scale, you need to understand the other subjects, which are igneous petrology, metamorphic petrology, and sedimentology as well. And for your information, any kind of national examinations in competitive examinations, they also provide this kind of interdisciplinary mixed up questions, not solely based on structural geology, not solely based on igneous petrology. I mean, there will be questions, but there are chances that they will mix up different kind of things to actually see how you are judging. I mean, how you're building up your concepts and linking one subject to the other, right? So this was all about course, week 1. I had 10 questions prepared and everyone interacted beautifully. I very much enjoyed having this live session. I am hoping to see you guys all in the next session next day. So for the plan for the next live session, we have the geometrical measurements and attributes of structural features and their stereographic projection. So we will do a lot of numerical problems in the next lecture, and we will also solve some geometric problems as well. So that's it. And since it is very 6:10 past 6, I thank you all for eagerly and paying attention to this live session, and thank you very much. Okay, so about the material, so these discussion sessions will, I mean, my job is to deliver today's recording and the lecture material to the NPTEL coordinator, and they will, I mean, create accordingly. I mean, they will provide you the materials accordingly. I don't have the direct access to provide you these kind of materials. My job is to record the lectures, take the live sessions, give the provide the lectures and the recordings uh, to the NPTEL coordinator, and they will decide further. So, but I insist you all to join the Q&A session. In the course dashboard, you will find Q&A. If you have any question, right there, I will be there to answer your questions because I will be handling that session. So anytime if you have any question while solving the assignments or seeing any kind of lectures from different weeks, feel free to drop a message there. You have to sign in through your Google account, and I will be also there. I get notified every time you guys post a question, so I will answer those things in that chat box. Okay. So thank you for joining today's live session, and I am stopping this sharing screen sharing mode, and thank you for joining. I'm closing the meeting. Bye.
Thank you, sir.
Yeah, thank you.
Thank you,
Thank you,
sir.
sir.
Yeah, thank you.